Light is the fastest messenger in the universe. For more than 13 billion years, it has crossed unimaginable distances to tell us the story of distant stars and galaxies. But what if there are distances that even light can never cross? Not because light is too slow, but because space itself is pulling apart faster than any signal can travel. This is the story of the absolute limits of the universe. What if the fastest thing in existence still cannot reach everything? Light is the universe's quickest messenger. Yet the deeper we look, the more we meet a quiet truth that feels almost unsettling. There are distances that light can never cross. Not because light is weak, but because space itself can stretch and separate faster than any beam can chase. In Einstein's relativity, the speed of light stands as a profound boundary for motion through space. And that boundary is so reliable that it becomes a ruler for reality. Yet cosmology adds a twist that sounds like poetry and math at the same time. The ruler keeps its length, while the page it measures keeps expanding. Imagine drawing 2 dots on a balloon, then inflating it. The dots recede even though neither dot is running. In our universe, far galaxies can recede from us because the fabric between us grows, and beyond a certain distance, the expansion wins forever. That is why the observable universe is not the same as the whole universe. It is the part whose light has had time to arrive since the beginning. It also means there is a kind of horizon, a cosmic limit where events can happen and remain unreachable in principle. To make this feel real, picture shouting across a river that is widening faster than your voice can travel. You can shout forever, yet the sound never arrives. Or imagine a lighthouse on a shoreline that is sliding away as the ocean grows between you. The lamp still shines, but the distance increases so relentlessly that your future will never include that beam. We have a smaller and more dramatic example nearby in the idea of a black hole, where a boundary called the event horizon marks the point of no return. Light itself cannot climb out once it crosses. That local horizon is a powerful metaphor for the larger cosmic horizon, not because the universe is a black hole, but because nature sometimes draws lines that no effort can erase. When I think about these limits, I hear Carl Sagan whispering a humbling reminder: we are made of star stuff. I also hear Neil deGrasse Tyson warning us with bracing honesty. The universe is under no obligation to make sense to you. And I remember Stephen Hawking urging a posture that feels almost like meditation. Look up at the stars and not down at your feet. Taken together, these voices point to the same lesson. Our reach is finite, but our curiosity can be infinite. The fact that some distances are forever uncrossable does not cheapen discovery. It purifies it. It tells us to value the light that does arrive. The photons that have traveled for billions of years to land softly on a detector built by minds made from ancient stars. My own view is that this boundary is not a wall meant to discourage us. It is a horizon meant to teach us proportion, patience, and reverence. We do not need to own the whole universe to be transformed by it. We only need to keep looking honestly at what can be known, and to accept with quiet courage what cannot. Have you ever wondered what it would mean if the universe had a built-in speed limit that nothing with mass can ever reach? The moment you ask that question, you are already stepping into the territory where physics stops feeling like a classroom and starts feeling like a quiet meditation on reality itself. Light moves in vacuum at exactly 299,792,400 158 meters per second, which is about 300,000 kilometers every single second. That number can sound like a cold statistic, but it is one of the most intimate facts we know about the cosmos. It tells you how quickly the universe can share a story, how fast a cause can become an effect, and how tightly space and time are stitched together. The physicist, James Clerk Maxwell, found that the equations of electricity and magnetism predict waves that move at a fixed speed. When scientists realized that this predicted speed matches the measured speed of light, the implication was breathtaking. Light is not just something that travels through space. It is a clue to what space allows. And then came Einstein. In the early 20th century, he took a simple idea and let it reshape everything. In his work on relativity, he treated the speed of light as a constant that does not change even if you move toward the light or away from it. In a widely read translation of his writing, you find the crisp statement that every ray of light moves in the moving system with the same velocity. That line is more than a technical claim. It is a turning point in human thought. Because if light always keeps the same speed for every observer, then something else must give. Time must stretch, lengths must contract, and simultaneity must become less absolute than our intuition wants it to be. The universe does not bend the speed of light to fit our common sense. It bends our common sense to fit the speed of light. This is why the speed of light is often described as the cosmic speed limit. Not as a rule written on a signboard somewhere, but as a deep consequence of how space-time is built. A simple and reliable way to say it is that nothing that carries information can outrun this speed through space. Even the modern definition of the meter is tied to this constant, because we trust it that much. Institutions that define measurement standards often explain it in plain language by saying that nothing in the cosmos, not matter, not energy, not information, can travel faster than light. That is not just poetry. It is measurement culture turning into worldview. Now, to feel how fast light really is, you need images that your mind can hold without breaking. In a single second, a beam of light could circle Earth more than 7 times. If you blink and your blink lasts about 1/10 of a second, light could still wrap around the planet almost once before your eyelids fully meet. The moon is roughly 384,400 kilometers away. Light needs a little more than 1 second to cross that gap. So when you look at the moon, you are always seeing it slightly in the past. The sun is about 149,600,000 kilometers away. Sunlight takes a little over 8 minutes to reach your skin and warm your face. That means every sunrise is a message that left the sun minutes ago. And yet it feels immediate because our nervous system lives on slower clocks than the cosmos. Push farther, and the numbers become almost spiritual in their scale. Light from Neptune takes several hours to reach Earth, depending on where the planets are in their orbits. Light from the nearest star system beyond the Sun takes more than 4 years to arrive. So the night sky is not a picture of now. It is a museum of time. Each point of light is a timestamp floating in darkness. And still, for all its speed, light is not fast enough to erase distance. It does not make the universe small. It reveals how large the universe truly is. Here is where relativity adds a second layer of wonder. The speed of light is not only a speed through space, it is also the conversion factor between space and time in the geometry of space-time. In everyday life, we treat distance and duration as different kinds of things. But deeper physics quietly shows that they are interwoven. If you try to push a massive object closer and closer to light speed, it resists in a very particular way. From the outside perspective, it takes more and more energy to gain the same extra fraction of speed. The closer you get to this limit, the more extreme the demands become. This is not a moral lesson about ambition. It is a structural fact about the universe. There is a calm finality to it, like a shoreline you can approach but never step beyond. Imagine you are in a spacecraft and you shine a flashlight forward. No matter how fast your ship moves, you still measure the beam racing away from you at the same light speed. That sounds impossible at first, because we are trained by daily experience to add speeds together. But nature insists on a different arithmetic here. What changes instead is time itself and your sense of what is simultaneous. This is also why modern technology quietly depends on relativity. The positioning system in your phone works because engineers account for relativistic effects on satellite clocks. Without those corrections, your location would drift by kilometers over time. So the speed of light is not only a distant cosmic principle, it is a daily companion hidden inside ordinary life. And still, the most human way to talk about the speed of light is to admit what it does to our imagination. It draws a boundary that turns the universe into a place of horizons. When you hear that light has been traveling for billions of years from a distant galaxy, you begin to feel how patient reality is. You also begin to feel how limited any single lifetime must be. I find a quiet comfort in that limitation. In a world that urges us to rush, to maximize, to keep up, the universe reminds us that some distances cannot be hurried. Even light does not cheat its way across space-time. It simply goes as fast as the rules allow. That becomes a lesson worth carrying into ordinary days. There is a difference between urgency and depth, and the cosmos rewards depth. It asks for patience in the face of scale, and humility in the face of limits. Because, when we understand the speed of light, we are not just learning a number. We are learning the shape of causality, the reach of information, and the tempo of the universe itself. When you look up at the stars, you are watching time travel in the only direction nature permits. Photons that left their sources long ago arrive now and touch your eyes with perfect consistency. And that consistency leaves us with one final question. If even light cannot make the universe fully reachable, what does that say about the limits of our knowledge, and the vastness that still lies beyond our understanding? Have you ever wondered whether distance is truly a thing you can trust? Not the distance on a map or the distance between two cities, but the distance between galaxies that look like calm lanterns in the dark. We tend to imagine space as a silent stage where objects move while the stage stays still. Yet the most unsettling idea in modern cosmology is that the stage itself is alive, stretching, breathing, quietly changing the meaning of far and near. Once you accept that space expands, you begin to see why distance in the universe is not fixed, like a metal ruler, and why the separation between galaxies can increase so rapidly that it can be described as faster than light without violating the core rule that nothing locally outruns light. This is where Einstein's insight becomes more than equations. It becomes a new way of seeing reality. As he famously said, "Space and time are not conditions in which we live, but modes by which we think." In that spirit, distance is not merely a number. It is an evolving relationship shaped by the geometry of space-time itself. To picture this, without fear of jargon, imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot sees other dots drifting away. And the farther apart two dots are, the faster their separation grows. No dot needs to speed across the rubber to make this happen, because the rubber is what changes. The same gentle logic applies to galaxies on the fabric of space, especially when they are far enough apart that gravity no longer binds them into the same local family. Or imagine raisin bread rising in the oven. The raisins do not crawl through dough, yet as the dough expands, each raisin becomes more distant from the others, and the ones already far apart separate the fastest because there is more dough between them stretching at once. These images are imperfect, but they give your mind a handle, and sometimes a handle is all we need to stop resisting a truth that feels impossible. Now comes the line that often shocks people. The distance between faraway galaxies can grow at a rate that exceeds the speed of light. That sentence sounds like a violation, until you realize what it does and does not claim. It does not say a spaceship in one galaxy is locally flying past a beam of light next door. It says the space between two far regions can expand in such a way that their separation increases extremely quickly. Light still keeps its local crown as the ultimate speed limit for anything moving through space in a local frame. Yet the universe can still widen the gap because it is not asking objects to break the limit. It is stretching the path itself. If you want a down-to-earth analogy that hits hard, imagine walking forward on a moving walkway that is carrying the floor backward under you. You can walk at your maximum pace, but if the walkway accelerates enough, you will still be pulled away from your destination. In this story, your legs are like any signal trying to cross a gap, and light is the fastest runner possible. But if the walkway is the expanding space between you and the exit, there can be a point where even the fastest runner cannot reach the far side, because the far side is receding faster than the runner can gain ground. This is not just a clever picture. It has a real consequence that feels almost emotional when you fully absorb it. There are regions of the universe we can see today because their light began its journey long ago, when they were closer in a younger universe. But there can also be regions so distant that light emitted there today will never reach us in the future. The universe can create a kind of horizon not made of walls or fog, but made of expansion itself. It is as if the cosmos draws a boundary around what can ever be in causal contact with us. Not out of malice, but out of geometry. In moments like this, I often remember Carl Sagan's calm acceptance of mystery. Somewhere, something incredible is waiting to be known. The boundary does not cancel wonder. It concentrates it. Because if there are distances light can never cross from now on, then every photon that does arrive is a kind of miracle of timing, a message that made it through while the corridor was still open. To make this even easier to feel, imagine you are sending a paper boat down a river toward a friend. The boat drifts at a steady speed, but the river splits into channels that pull water apart more and more as they go downstream. At first, the boat can still reach your friend's side, but after a certain point the separation between channels becomes so wide that no matter how many boats you release, none will cross to the other channel again. Light is our paper boat, and expanding space is the river that changes its own shape with time. Or picture a rubber band stretched between your fingers and your friend's fingers. If you begin pulling your hands apart, while a tiny ant walks along the band at a fixed top speed. There is a point where the band lengthens faster than the ant can walk, and the ant will never reach the other side, even though it never slows down and never breaks any rule of its own body. That is what distance is not fixed means in a visceral way. Far is not just far. Far can become unreachable because the bridge is stretching under the traveler. When people first hear this, a natural reaction is a kind of existential chill, as if the universe is taking things away from us. But I do not interpret it that way anymore. I see it as a lesson in intellectual honesty and a quiet invitation to gratitude. Because the expanding universe teaches us something that is both scientific and deeply human. Limits exist, and they are not always negotiable. Yet within limits there is still vast space for meaning, for curiosity, for care. We cannot demand that the cosmos be fully accessible to our species, but we can choose to become wise within the horizons we inhabit. This is where my personal view becomes simple. The value of knowledge is not measured by whether we can know everything, but by whether we can listen well to what the universe is willing to show us now. And what it shows us is astonishing. Every time a telescope collects ancient light from a distant galaxy, we are witnessing a collaboration across time between that galaxy's past and our present. We are reading a chapter that survived billions of years of cosmic stretching to arrive at our detectors. Stephen Hawking once reminded us, "Remember to look up at the stars and not down at your feet." In this topic, that advice feels literal, because looking up is not just romance. It is the act of receiving messages that have traveled through an expanding universe that did not have to deliver them to us. The fact that we can reconstruct cosmic history at all is astonishing when you remember that distance itself has been changing the whole time. So yes, in the deepest sense, distances in space are not fixed, and the separation between galaxies can grow at an effective rate that exceeds the speed of light because the space between them expands. But the emotional conclusion is not despair. It is clarity. The universe is not a static museum where everything waits patiently to be visited. It is an unfolding story whose pages move, even as we read. The lesson I take from this is a quiet one. Do not postpone wonder. Do not assume tomorrow will always have the same window as today. Because even cosmically, windows can close, horizons can form, and what is reachable now may not remain reachable forever in principle. That thought does not make me feel small. It makes me feel awake. Awake to the rare privilege of living in a time when the universe still sends us light from across unimaginable distances, and we still have the minds to ask what it means. What if there is a limit to how far reality can ever speak to us? Not because our instruments are weak, but because the universe itself draws a quiet line and says no further. When we ask what the cosmic horizon is, we are really asking how much of existence can ever become experience. How much of the universe is allowed to leave a trace in our detectors, in our equations, in our stories. The cosmic horizon is not a wall at the edge of space. It is a boundary in time, written by the finite age of the universe and the relentless expansion of space-time itself. It marks the farthest distance from which light has had enough time to reach us since the universe first became transparent. Everything beyond it may exist as fully and vividly as our own cosmic neighborhood, yet it remains silent to us. Not hidden by choice, but unreachable by law. In everyday life, distance feels simple. If something exists, you can eventually walk toward it or send a signal. But the universe does not obey that intuition. In cosmology, distance is braided with time, and knowledge travels only as fast as light allows. Every star you see is already a memory. Every galaxy a message delayed by millions or billions of years. To understand the cosmic horizon, imagine the universe as a dark ocean at night, and light as small boats carrying news. Some boats departed their shores billions of years ago, and only now arrive at our instruments as faint whispers. Others are still traveling, their messages on the way. And beyond a certain distance, there are shores whose boats have not yet arrived, and may never arrive at all. This distinction matters deeply, because it separates what is unseen from what is unknowable. The universe has a history of about 13.8 billion years. That fact alone already limits how far light could have traveled. But the cosmic horizon is not simply 13.8 billion light-years away, because space itself has been expanding while the light was moving. As photons crossed the cosmos, the distances between galaxies stretched beneath them. The destination kept receding, like walking toward a lighthouse while the pier beneath your feet slowly lengthens without end. This is why the observable universe is vastly larger than a naive calculation would suggest. The horizon is not a static circle. It is the result of a long negotiation between time, motion, and expansion. Here the idea becomes both precise and strangely intimate, because when you look farther into space, you are not just seeing farther away. You are seeing further back in time. When you look at the moon, you see it as it was a little more than a second ago. When you look at the sun, you see it as it was 8 minutes ago. When you observe a galaxy millions of light years away, you are watching light that began its journey before human civilization existed. And as your gaze approaches the cosmic horizon, you are peering into an era when the universe itself was young, hot, dense, and unfamiliar. In this sense, the horizon is a museum of time, where distance becomes memory. It is also a profound lesson in humility, because no amount of technological ambition can erase it. You can build larger telescopes, cool detectors to fractions of a degree above absolute zero, and refine your theories with exquisite mathematics. But you cannot make the universe older, and you cannot persuade light to arrive sooner than the laws of nature permit. The cosmic horizon does not exist because we are weak. It exists because the universe has a structure. This is why it feels less like a failure of science and more like a boundary condition of reality itself. And yet, within that boundary, the amount we can learn is astonishing. In a single night of observation, we can collect photons that began traveling long before Earth formed. We can decode those photons into temperature, composition, motion, and age. From faint, spectral lines, we reconstruct the life cycles of stars, the assembly of galaxies, and the emergence of structure from an almost perfectly smooth early universe. The horizon does not shrink our knowledge, it concentrates it. It tells us exactly where evidence ends and speculation must begin. To make this intuitive, imagine a campfire burning in a vast dark field. Light spreads outward at a fixed speed, forming an expanding sphere of illumination. Now imagine that the field itself is stretching as the light travels, so some distant regions are pulled away faster than the light can reach them. Those regions are not hidden by darkness. They are hidden by geometry. The cosmic horizon is the edge of that illumination, not because the fire is weak, but because space itself is dynamic. There is another example that feels closer to human experience. Imagine waiting for a message that was never sent. You can speculate endlessly about its contents, but without the signal, you have no evidence. Beyond the cosmic horizon, the universe may be filled with galaxies, events, and histories. But their signals have not had time to reach us, and some never will. This is not a statement of loss. It is a statement of causal order. It tells us how a finite age and an expanding space-time divide reality into the reachable and the unreachable. Great thinkers have long warned us that mystery is not a flaw but a feature of understanding. Albert Einstein once said that the most beautiful experience we can have is the mysterious. The cosmic horizon safeguards that mystery not by hiding it behind secrecy, but by placing it beyond causal contact. Carl Sagan reminded us that we are a way for the cosmos to know itself. If that is true, then the horizon marks the limits of what the cosmos can know through us at this moment in its history. And as Neil deGrasse Tyson often emphasizes, the universe is under no obligation to make sense to us. The horizon is one of the clearest expressions of that truth, a reminder that nature does not arrange itself for human completeness. When I reflect on this idea, I feel both awe and calm frustration. Oh, because light can cross billions of light years and still arrive intelligible enough for us to understand its origin. Calm frustration, because some answers are not waiting behind doors we can open. They are waiting beyond horizons that are not doors at all, but geometry. This realization does not weaken science. It strengthens it. It teaches honesty, discipline, and restraint. It reminds us to distinguish clearly between what is measured, what is inferred, and what is imagined. The cosmic horizon also reshapes how we think about meaning. It tells us that knowledge is precious precisely because it is limited. Every photon we receive is a gift from a past we never lived. Every observation is a message in a bottle that survived a long journey through an expanding universe. The presence of horizons does not end the adventure of discovery. It defines it. You do not need access to everything for exploration to matter. You need clarity about what can be known, and respect for what cannot. So when you look up at the night sky, do not think of the cosmic horizon as a limit that diminishes us. Think of it as a boundary that gives shape to wonder. Without boundaries, stories dissolve into noise. With boundaries, every faint galaxy becomes meaningful. Every measurement becomes an act of courage. And every unanswered question becomes a quiet meditation that keeps the human spirit awake. Have you ever wondered if there is a border in reality where the universe continues, yet the story of it can never reach us? We look up and feel that the night sky is an open book, but physics quietly reminds us that every page we can read is limited by time, by speed, and by the swelling of space itself. When people say the universe is vast, they usually imagine a bigger telescope will solve the problem, as if distance were only a matter of patience. Yet there is a deeper limit that does not care about patience at all, a limit that lives not in our instruments, but in the geometry of the cosmos. This is where the idea of a cosmic event horizon enters like a calm and sobering breath, because it separates two truths that feel similar but are not the same. The observable universe, which is everything whose light has had time to reach us since the beginning of cosmic history, and the larger universe beyond it, which may exist abundantly yet remain forever out of contact with Earth. The first truth is a window. The second is a silence. And the silence is not emptiness. It is simply a region whose messages will never arrive. To understand this without losing the wonder, imagine you are standing on a beach at night, watching distant ships flash their lights across the water. Some flashes reach you immediately. Some arrive faintly after a long stretch of darkness. Now change the beach itself into something alive that is stretching while you watch. So the ships are being carried away not by their engines but by the sea widening beneath them. At first you still receive their signals, because the light can cross the growing distance. But far enough out, there comes a point where the sea expands so relentlessly that the flashes can never close the gap. The ships exist. Their lamps still shine, yet their light will never touch your eyes again. That is the emotional core of a cosmic event horizon. A boundary defined, not by darkness in the source, but by the fate of the space between you and the source. This is where language can trick us, because we often hear that nothing can move faster than light. That statement is true for objects moving through space in the usual sense. But general relativity allows space itself to expand, and that expansion can increase distances at an effective rate that exceeds the speed of light without any object locally breaking the rule. The galaxies are not racing through space like bullets. They are largely being carried by the stretching fabric of space. This is why cosmology can honestly say two things at once. Light remains the universal speed limit for local motion. And yet, some regions recede from us so quickly that light emitted today from here will never catch up to them. Now we can draw the critical distinction with a gentle precision. The observable universe is not the whole universe. It is the part from which light has already arrived within the age of the universe. It is a sphere of information, not a sphere of existence. When you see the cosmic microwave background, you are seeing a relic signal from a time when the universe first became transparent, a kind of ancient afterglow that has been traveling to us for almost the entire cosmic lifetime. The fact that it arrives at all is an astonishing gift of physics, because it means the universe kept a memory and delivered it across billions of years. Yet even as this observable region is immense, it is still only a region defined by what has had time to reach us. Beyond that is more universe that may be teeming with galaxies and events, but whose light has not reached us yet. And then beyond that is an even more severe limit, the cosmic event horizon, which marks the boundary beyond which events will never be able to affect us in the future. Not later. Not with better telescopes. Not with more patience. Never. If you want an image that is almost painfully simple, picture a message in a bottle tossed into an ocean that is not merely wide but expanding every second. If the expansion is gentle enough, currents and time can still bring the bottle to shore. But if the ocean is expanding too fast in the relevant direction, the shoreline can recede from the bottle faster than the bottle can drift. The bottle can float forever and still never arrive. In our universe, photons are the bottles, and the expansion of space is the ocean that decides their fate. At this point, it helps to anchor the feeling with voices that have carried cosmic ideas into human language with unusual clarity. Edwin Hubble expressed the strange simplicity of the pattern when he wrote that the most striking feature of the data is the linear relation between distance and velocity. That relation is now a foundation of modern cosmology, and it hints at why the far universe can slip beyond reach. Albert Einstein once confessed that the most incomprehensible thing about the universe is that it is comprehensible. In the context of horizons, that line becomes bittersweet, because it suggests our comprehension will always be partial, not due to failure of mind, but due to the structure of space-time itself. Stephen Hawking warned that even if you think you are lost in the universe, there is always something you can do and succeed at. Here, the success is not in conquering the horizon, but in understanding it and letting that understanding refine our humility. And Carl Sagan gave a sentence that feels almost designed for this subject when he said that somewhere, something incredible is waiting to be known. The horizon tells us that some incredible things may be waiting beyond what we can ever know directly. And yet the desire to know remains one of the most human lights we possess. To keep the concept concrete, consider 3 everyday style examples that map cleanly onto the science. First, think of a city at night seen from a mountain. The lights you can see are limited by the curve of the earth and the clarity of the air. The city does not end at the line of sight. Only your access to it does. Second, think of thunder and lightning in a storm far away across a plain. You may see the flash but never hear the thunder if you walk away faster than the sound can travel through the air to you. The storm is real. The signal is real. But the medium and your motion decide what reaches you. Third, think of an internet live stream on a connection that keeps degrading while the broadcaster moves farther away. Eventually the stream can drop permanently, not because the broadcaster stopped, but because the channel can no longer carry the signal to you. In cosmology, space itself is the channel, and its expansion can cut off the signal forever. Now let the mind rest on the difference between seeing and reaching. It is one thing to say we cannot travel to a galaxy because it is too far given our technology. It is another thing to say that even light emitted now from that galaxy will never arrive here because expansion prevents it. That second statement is what makes the cosmic event horizon so profound, because it is a limit not of engineering but of causal connection. It is a boundary in what can influence what. If the universe continues to accelerate in its expansion, as observations strongly suggest through the idea commonly called dark energy, then more and more galaxies will drift beyond this horizon over immense spans of time. From the perspective of far future observers in our local group of galaxies, the night sky may grow lonelier as distant galaxies fade and slip away. Not because they vanish in reality, but because their light becomes stretched and weakened and finally unable to overcome the swelling, separation. The universe does not become smaller. Our accessible universe does. This is also why the phrase observable universe must be handled with care. People sometimes hear it and assume it means everything that exists. But it is better to hear it as everything that can be observed from here given the age and physics of our cosmos. It is a map drawn by light travel time and cosmic history. And a cosmic event horizon goes further by drawing a map of what can ever be observed or affected in the infinite future from our location. You can think of it as the ultimate boundary of possible conversations with the cosmos. Messages from beyond it are not merely delayed. They are excluded by the future behavior of space-time. If this sounds cold, it can also be strangely comforting. There is a meditative lesson hidden here, one that does not diminish science but deepens it. Our knowledge is shaped not only by curiosity but by horizons. Yet within our horizon is already a universe so rich that a single human lifetime cannot exhaust its wonders. We have learned to read the spectrum of starlight and infer chemical elements from worlds we cannot touch. We have learned that the faint microwave glow across the sky is a fossil whisper from the early universe. We have learned that gravity can bend light into arcs and rings, so we can weigh invisible mass across cosmic distances. These are triumphs of mind over distance, even when distance keeps its final secrets. So when you hear the phrase cosmic event horizon, do not imagine a wall of darkness. Imagine instead a subtle rule written into the expansion of the universe. A rule that divides existence into what can one day meet us, and what will forever remain elsewhere. It is not a tragedy. It is a condition of being inside a universe with history and growth. And it invites a final reflection that holds both awe and restraint. If there are regions of the universe that will never share their light with Earth, does that mean reality is richer than any possible science? Or does it mean science is even more miraculous for extracting truth from the thin slice of light we are allowed to receive? How can anything outrun light when light is supposed to be the ultimate speed limit? That question feels like a trap, because we have all heard the rule that nothing can travel faster than light. Yet when cosmologists say distant galaxies can recede from us faster than light, they are not breaking physics. They are showing you what the rule really means. In Einstein's relativity, the speed limit applies to motion through space locally, to anything that tries to move past its nearby surroundings faster than light. It does not forbid space itself from changing, stretching, or expanding. That difference sounds subtle, but it is the difference between a paradox and a clean explanation. Imagine standing on a calm ocean at night, watching two distant buoys drift apart as the tide pulls water outward. If you only stared at the buoys and refused to think about the water between them, you might swear the buoys were racing away by their own power. But the ocean is doing the work. Cosmic expansion is like that, except the ocean is the fabric of space itself. This is why a line that sounds impossible becomes ordinary in modern cosmology. Galaxies can have a recession speed faster than light, without any galaxy locally breaking the light speed limit. They are not blasting through space like rockets, ignoring Einstein. The space between us and them is growing. The most famous way to picture it is the balloon analogy, with little dots drawn on the surface. As the balloon inflates, every dot sees other dots move away, and the farther a dot is, the faster it recedes. No dot is special. No dot is the center on the surface, and no dot is violating a speed limit on the rubber it sits on. The stretching surface creates the increasing separations. A second analogy is raisin bread in the oven, where raisins separate as the dough expands. Each raisin is mostly just sitting there in its local dough, but distances between far raisins grow quickly because more dough lies between them to expand. Now replace dough with space and you are close to the real idea. Relativity is strict about what happens locally, in your neighborhood of space-time. If a spaceship passes you, you can measure its speed nearby, and you will never measure it exceeding light in your local frame. That is the core prohibition. But recession speed in cosmology is not the same as a local speedometer reading. It is a way of describing how fast the distance between far separated regions increases as the cosmic scale changes. Those regions are so far apart that there is no single shared local frame covering both at once. So the familiar rule must be applied with care. If that sounds like wordplay, it is not. It is geometry. General relativity is not just a set of speed rules. It is a theory of space-time itself. John Archibald Wheeler captured the heart of it with a line that physicists still repeat because it is so precise and so poetic. Space-time tells matter how to move. Matter tells space-time how to curve. When space-time curves and evolves, it changes what we mean by distance across the cosmos. And because the universe is expanding on large scales, the distance between you and a very remote galaxy can increase faster than light could cross that growing gap. This does not mean information is traveling faster than light between you and that galaxy, and it does not mean you can send a message that arrives instantly or even at all. The light speed limit still protects causality locally, which is the true reason the limit matters. To make this feel tangible, picture a moving walkway at an airport that is slowly lengthening while you try to walk to the far end. Your walking speed is limited. You cannot sprint beyond your physical maximum. But if the walkway is being extended ahead of you fast enough, the end can retreat from you, even if you never slow down. You are not breaking a speed limit. The path is changing. Cosmic expansion can do the same to light. Light always moves at light speed locally, but the space it must cross can keep growing while it travels. In the real universe, this depends on how the expansion rate evolves with time, and it leads to one of the most mind-bending consequences of modern cosmology: cosmic horizons. There are distances so vast that light emitted today from beyond a certain boundary will never reach us, because the intervening space expands too quickly on average. This is not a failure of light. It is a statement about the universe's history and its future. You can feel the emotional weight of that if you pause, because it means the universe can contain events that are real and yet forever sealed away from our observation. Not hidden by dust or darkness, but separated by the evolving geometry of space-time. And still, the rules remain clean. No galaxy is locally outrunning its own light beam next door. No signal is cheating causality in a lab. No information is teleporting across space. The expansion is not motion through space in the ordinary sense. It is the stretching of the metric that defines distances in the first place. If you want a crisp everyday image for that metric idea, think of a map printed on elastic fabric. Two towns drawn on the cloth do not need to slide across the surface for their separation to change. You only need to stretch the cloth uniformly. The towns stay put on the material, yet the ruler distance between them increases. That is what cosmologists mean when they say galaxies are carried along with the expansion on large scales. Of course, the universe is not made of rubber and ink, and galaxies are not glued down by magic. Gravity binds local structures strongly enough that expansion does not tear apart your body, the Earth, or the solar system. Even a galaxy like the Milky Way is held together by gravity and does not expand like the cosmic average inside its own bound region. So when you hear faster than light recession, you should imagine the grandest scales only. The web of galaxies between clusters where the universe is smooth enough to be described by an expanding geometry. The famous relation that farther galaxies recede faster captures that large-scale behavior, and it is why extremely distant galaxies can have recession speeds exceeding light when described in that global way. If you sit with the idea long enough, it starts to feel less like a trick and more like a quiet truth. The universe is not a stage where objects move under fixed lights. The stage itself evolves. That is why cosmology can sound like poetry without losing rigor. And this is where trusted voices help anchor the feeling to the science. Wheeler's line about space-time and matter is one anchor. Another is Carl Sagan's reminder that discovery begins with humility and wonder. Somewhere, something incredible is waiting to be known. The faster-than-light expansion story is exactly that kind of incredible thing. Not because it breaks the rules, but because it reveals the deeper shape of the rules. Neil deGrasse Tyson has a sentence many people remember for the same reason. The universe is under no obligation to make sense to you. At first glance, faster than light, expansion does not make sense to human intuition built for roads and rivers. But once you accept space-time as dynamic, the pieces click into place, and the universe begins to make a different kind of sense. A sense that is more geometric than mechanical, more like a living tapestry than a rigid grid. Now let us bring it down to a few simple scenarios you can hold in your mind when you speak to an audience. First, imagine two friends standing still on opposite ends of a long elastic band. They do not walk. They do not run. You stretch the band smoothly, and the distance between them increases, even though neither friend is moving through the band locally. Second, imagine ants on a balloon surface. Each ant can crawl at a limited speed. If the balloon expands fast enough, two faraway ants can separate faster than any ant can crawl, even though each ant is still crawling within its own local limit. Third, imagine a flashlight beam trying to reach a far shoreline while the river widens as it flows downstream. The beam moves at light speed locally, but the widening gap can still prevent arrival if the widening outpaces the beam's progress in the long run. These are not perfect models, but they carry the intuition that the path can change, while the traveler obeys its own limit. From there you can gently return to the central clarity. Special relativity sets a limit for motion through space in local inertial frames. General relativity allows space-time itself to expand or curve. And in an expanding universe, the separation between distant co-moving points can grow at a rate that exceeds light when expressed as a recession speed across cosmic distances. The price we pay for this beauty is that horizons exist, regions of the universe that are forever beyond contact from our vantage point. Yet the gift we receive is profound, because within our horizon there is still an ocean of observable history, light that has traveled for billions of years to meet our eyes. Every photon that arrives is a meditation bell ringing across time, reminding us that understanding is not only about reaching everything, it is about seeing clearly what the universe allows and what it forbids. So the next time someone says the universe expands faster than light, do not picture lawlessness. Picture elegance. Picture a cosmos where the fastest messenger still keeps its promise, locally, while the very notion of distance evolves on the grandest scales. And then let the real hook linger in the listener's mind. If space-time can stretch so relentlessly that even light cannot cross certain gaps, what else about reality feels impossible only because we are still using the wrong intuition? Have you ever looked at a distant galaxy and wondered whether it is already slipping away from us forever? Not in a poetic sense of time passing, but in the strictest physical sense, that no beam of light we send today could ever reach it, and no light it emits tomorrow could ever arrive here. This question feels unsettling because it challenges one of our deepest intuitions. That light always wins. Yet, Modern cosmology quietly tells us otherwise. Not because light has slowed down, but because the universe itself is changing beneath it. For most of human history, the night sky felt eternal and stable. Stars appeared fixed, galaxies unknown. Distance meant effort, not impossibility. But when Edwin Hubble revealed that distant galaxies are receding from us, the universe transformed from a static stage into a dynamic story. And when later observations showed that this expansion is accelerating, driven by what we now call dark energy, a deeper implication emerged quietly. Some galaxies are not just far away, they are becoming unreachable. This does not mean they vanish in a dramatic cosmic event. They continue to exist, to form stars, to glow and evolve. What vanishes is the possibility of connection. Space between us and them expands so rapidly that even light emitted today can never close the gap. The photon moves faithfully at the maximum speed allowed by nature. Yet the destination retreats faster than the photon can advance. It is not a failure of light. It is a feature of space-time itself. To imagine this, think of walking up a long moving walkway in an airport. At first, you make steady progress. But imagine the walkway begins to accelerate in the opposite direction. You walk at your fastest pace, yet the end keeps moving away. No matter how long you walk, you never arrive. On cosmic scales, light faces the same challenge when the expansion of space accelerates beyond a critical point. Astronomers describe this limit as a cosmic event horizon. Not a wall in space, but a boundary in time and causality. Beyond it, events can occur that will never influence us. There are galaxies whose ancient light still reaches our telescopes today, allowing us to see them as they were billions of years ago. Yet those same galaxies are already so distant now that any light they emit in the present will never arrive here. They exist for us only as memories, frozen in photons launched long before the universe grew too wide between us. Carl Sagan once said that the universe is not required to be comprehensible to us. This truth feels especially sharp here, because it reminds us that observation itself has limits that no technology can overcome. Stephen Hawking often urged us to look up at the stars and understand them. But understanding does not always mean reaching. Sometimes it means accepting a horizon and learning from its shape. Imagine standing on a shoreline at night, watching distant ships slowly drift away. At first, their lights grow dim. Later, the horizon hides their hulls. Eventually, even the lights disappear. The ships do not cease to exist, but the ocean between you grows too vast for sight or signal. In the universe, accelerated expansion plays the role of that growing ocean. This realization reshapes how we think about the observable universe. What we see is not all that exists, only all that light has managed to bring to us so far. The observable universe is a bubble defined by time and speed. And as time goes on, that bubble does not necessarily grow to include everything. Instead, parts of the universe slip permanently beyond its edge. There is something deeply humbling in this. It tells us that our cosmic story is written within boundaries we did not choose. Yet it also adds meaning to every observation we make. Every photon that reaches our detectors is a survivor, a message that crossed space before the door quietly closed behind it. astronomy becomes not just a science of distance, but a science of timing. And still, this is not a story of loss alone. Gravity binds nearby galaxies together, forming islands of connection that will endure even as the wider universe accelerates away. Our local cosmic neighborhood remains rich and interactive, reminding us that meaning does not require infinity, only relationship. Albert Einstein spoke of wonder as the foundation of true understanding. In confronting distances that even light can never cross, we encounter that wonder in its purest form. Not as ignorance to be erased, but as a horizon that gives shape to knowledge. So when you hear that some galaxies are already beyond any possible future contact, do not imagine the universe tearing itself apart. Imagine instead a slow and silent widening, a calm expansion that changes what is reachable without destroying what exists. Imagine photons leaving distant stars tonight, traveling faithfully through their local space, obeying every law of physics, and yet destined never to arrive here because the path itself keeps growing beneath them. And let that thought return you gently to the present, to the light that does arrive, to the stories we can still read, to the universe that allows itself to be known at all. Because if some distances are truly uncrossable, then every glimpse we receive is not ordinary. It is precious. And the question that remains is not whether the universe hides parts of itself from us, but whether we are brave enough to accept that mystery without pretending our limited view is the whole truth. What if the most brilliant flash you can imagine could be trapped forever, not slowed down, not weakened, but simply refused an exit by the geometry of space itself? A black hole is that kind of question made real. A place where the universe stops negotiating and starts drawing a boundary so strict that even light cannot cross it from the inside out. We often speak of distance as if it were only a matter of how far you travel. But a black hole teaches something stranger and more intimate. There are separations that are not measured in kilometers, but in the very shape of time and space around you. In everyday life, a wall blocks you because it is solid. A locked door blocks you because it is closed. And a storm blocks you because it is dangerous. In a black hole, the barrier is none of those things. It is a horizon, a line in space-time beyond which all roads forward point inward. Once that idea lands in the mind, it does not feel like a simple fact anymore. It feels like a meditation on limits, on what the universe allows and what it does not. The boundary has a name that sounds almost poetic: the event horizon. It is called that because events inside it cannot affect the outside world. Not later, not after a long delay, not with better engines or cleverer routes. The sentence is absolute. If you are inside, the outside cannot receive your light. That is why this is such a clear example of a distance light can never cross, and why it matters to the larger question of cosmic horizons. Because here, the limit is local, carved into a region of space you could in principle point to on a star map. Black holes are not magic holes punched through reality. They are solutions of gravity pushed to an extreme. When a massive star collapses after exhausting its fuel, or when enormous amounts of matter collect and compress over cosmic time, gravity can become so intense that escape becomes impossible. The key word is escape, because a black hole does not suck like a vacuum cleaner in a cartoon. Far away, it can behave like any other object of the same mass, with planets and stars orbiting it in stable paths. The drama begins only when you get close enough that the escape speed exceeds the speed of light. At that point, light itself can climb outward for a moment, but it never reaches freedom. It loses the race against the curvature of space-time. If you want a picture that helps the mind hold this without drowning in equations, imagine a river flowing toward a waterfall. Far upstream, you can swim across or paddle back easily. The water is moving, but you still have choices. Closer to the edge, the current accelerates, and you must work harder just to stay in place. Now imagine reaching a point where the river flows faster than the fastest boat you could ever build. Faster than any possible swim stroke. Faster than any engine nature allows. That point is like the horizon, not because the water is a physical wall, but because the direction of inevitability has taken over. The river analogy is imperfect, but it gives you a felt sense of what physicists mean when they say the horizon is not a surface you crash into. It is a boundary in what can influence what. There is another image that is even simpler. Imagine standing on a vast hillside covered in ice. At the top, you can still walk in any direction. Your feet grip enough to let you choose your path. But lower down, the slope becomes so steep and slick that every step you take carries you further downhill. And eventually you reach a point where every possible step forward leads down. The event horizon is like that tipping point, except the slope is not terrain. It is the structure of space-time itself. Past it, the future points inward, and escaping would require moving not just fast, but in a direction that no longer exists as an option. This is where the language becomes quietly profound. Because when physicists say you cannot go out, they are not merely saying you cannot move through space outward. They are saying the outward way is no longer part of your future. You can circle the idea like a candle in a dark room, and each pass reveals another facet. The horizon is local in the sense that it belongs to the black hole and its immediate neighborhood. Yet it is also universal in the sense that it is a law of causality made visible. It draws a circle around a region and says, beyond this line, cause and effect cannot travel outward. That is why it pairs so naturally with the broader cosmic story of horizons. The universe has limits not only at the edge of what we can see, across billions of light years, but also in pockets of space where gravity tightens the rules to their hardest form. If you have ever seen images from the Event Horizon Telescope of a dark silhouette surrounded by glowing gas, you have already witnessed the emotional power of this boundary. The darkness is not paint. It is not a cloud. It is not an absence of stars. It is the shadow of a place where light is not permitted to return to us. That shadow is one of the most astonishing achievements of modern observation, because it turns an abstract limit into a shape we can contemplate. Yet even that shape can mislead if we take it too literally, because the horizon itself is not a shining ring or a physical rim. It is the boundary from which the last possible photons struggle outward before being dragged back or swallowed in or redshifted beyond detectability. The notion that black holes are simple in a certain way has been summarized in a famous line by John Wheeler, a pioneer of relativistic physics and the man who helped popularize the very term black hole. He said, "Black holes have no hair." In that short phrase, he captured an astonishing truth, that a mature black hole can be described externally by only a few parameters, such as mass and spin and electric charge. Everything else about what formed it seems to vanish behind the horizon from the outside view. Another voice that shaped how the public imagines these objects is Stephen Hawking, who insisted that even our most fearsome cosmic monsters must obey quantum rules. He offered a line that is both playful and precise in spirit. Black holes are not so black. In the same breath of thought, we meet a paradox that deepens the story. Because if black holes can emit a faint radiation due to quantum effects, then the horizon is not only a one-way gate for light in a classical sense. It is also a stage where gravity and quantum physics whisper to each other in ways we still struggle to reconcile. That whisper is part of why black holes are not just dramatic astrophysical objects, but laboratories for fundamental physics. Yet even before we step into quantum mysteries, the local horizon already gives the listener something concrete to hold, because we can describe what would happen to light in a way that feels almost visual. Picture a lighthouse beam sweeping across a calm sea, each pulse traveling outward in expanding rings of photons. Now imagine the lighthouse placed near a black hole. The beam still leaves the lamp, but as it climbs away, it loses energy. Its wavelength stretches, and to a distant observer it reddens and dims. Closer still, those photons can be bent into arcs and halos, forming gravitational lensing that can make the background sky appear warped like glass. And at the boundary, the last rays that barely avoid capture can orbit for a time on precarious paths, circling like moths around a flame that is actually an absence of flame. One more step inward, and the direction that used to be outward becomes as unreachable as yesterday. This is where you can help the audience feel the scale without getting lost in numbers. By comparing two kinds of horizons they may already know. On Earth, there is a horizon at sea, a line that seems like an edge but is really a limit of sight due to curvature. You can sail toward it and it recedes forever, because it is not a wall. It is geometry and perspective. A black hole horizon shares the idea of geometry shaping what you can see, but it is far more severe, because it is not only a limit of sight, it is a limit of causation. You can approach it and not notice anything special at the exact crossing if the black hole is large enough, which is a detail that often surprises people. The catastrophe is not a bright boundary line. It is the change in what futures remain available. And that brings us to the heart of why this local horizon belongs in a story about distances light can never cross. In the vast universe, there may be regions receding from us faster than light because space itself expands, placing them beyond a cosmic event horizon. That can feel abstract, because it happens on scales so large that imagination slips and falls. A black hole offers the same lesson in a smaller frame, a pocket-sized demonstration of an absolute boundary, a reminder that the universe can create one-way separations not by building a fence, but by bending the rulebook of paths that light can take. If the audience wonders whether a black hole is just a dramatic special case, you can gently show that it is a theme that repeats throughout physics. There are always speed limits and information limits, and horizons are what those limits look like when the universe turns them into geography. Even in ordinary relativity, there is a kind of horizon for accelerated observers, where some signals can never catch up. The black hole is simply the most cinematic form of that idea, because it turns invisibility into a permanent condition. And the story becomes even more vivid when we connect it to something the listener already senses in their body: the relationship between time and escape. Imagine trying to send a message to a friend as you fall toward a black hole. You pulse a flashlight in a steady rhythm. To you, your pulses are regular, calm, even intimate. To your friend far away, those pulses arrive slower and slower, stretched out as if time itself is being diluted. The light is not just traveling through space, it is climbing out of gravity, and the climb changes the story it carries. The message fades not because you stop flashing, but because the universe edits the signal as it tries to leave. Eventually, from the outside viewpoint, the last light from near the horizon becomes so redshifted and so delayed that it effectively disappears into darkness. And then the silence becomes complete. That is a powerful bridge to a contemplative tone, because it invites the listener to notice how many of our everyday intuitions rely on the possibility of return. We throw a ball and it comes back. We shout across a room and the sound arrives. We send a signal and we expect an answer eventually. A black hole is a region where the expectation of reply is not just unlikely. It is forbidden by the structure of space-time. In a universe that otherwise feels open and continuous, that kind of absolute boundary can feel almost spiritual, like standing at the edge of a truth that refuses to be crossed. Kip Thorne, one of the leading theorists of black holes and gravitational waves, once emphasized how real and physical these objects are within general relativity, not as metaphors but as consequences of the equations that also explain the motion of planets and the bending of light. When you place his authority beside Wheeler and Hawking, the listener feels a lineage of minds turning the same gemstone of reality and finding it consistent from many angles. And then you can return gently to the main point. The black hole horizon is a local answer to a cosmic question. Yes, there are distances even light can never cross, and sometimes they are not far away at the edge of the universe. Sometimes they are here in principle, wrapped around a dark center within a galaxy. The most unsettling part is that the boundary does not announce itself with fireworks. It can be silent, smooth, almost gentle at the moment of crossing for a large black hole. The violence is not in the boundary itself, but in what the boundary means. It means that the universe can create a region where information has no route back to you, where the story ends not with destruction you can witness, but with absence you must accept. And acceptance is the quiet skill that this topic teaches if you let it. Not surrender to ignorance, but reverence for the fact that reality contains edges that are not edges of space alone. They are edges of communication and causality. In that sense, a black hole is not only an object in the sky, it is a lesson written into space-time itself. It tells us that some frontiers are not waiting to be crossed by better rockets, but waiting to be understood with deeper humility. And when you lift your eyes back from the local abyss to the grand architecture of the cosmos, the connection becomes almost unavoidable. If a black hole can place a horizon around a region of space, then the universe as a whole can place horizons around us too. Not out of cruelty, but out of the same lawful structure that makes light finite and time directional. The night sky then becomes not only a gallery of distant lights, but also a map of boundaries we live within. Some boundaries we can approach and measure, some we can photograph as shadows, and some we can only infer from what never arrives. If that feels unsettling, it is also strangely beautiful, because it means the universe is not obliged to be fully available to us. Yet it still leaves enough traces, enough bending of starlight and ripples of gravity and glowing rings of hot gas, for our minds to climb toward understanding. So the next time you hear the phrase event horizon, do not imagine a Trapdoor in space. Imagine a quiet line where the future points inward. And let the thoughts settle like slow breath. That somewhere out there, nature has drawn a circle in the dark and written a simple rule inside it. No light returns. Then ask yourself one last thing. If the universe can hide a region completely behind a local horizon, how many other horizons shape what we believe is real? And how confident should we be when we argue about what must exist beyond what can ever reach us? What if the universe you can see is not the universe that exists, but only the part that has had enough time to speak to you? This question does not attack science. It deepens it. Because the observable universe is not a claim about the size of reality. It is a claim about the reach of light in a universe that has a beginning, an age, and an ever-expanding fabric of space. Everything you have ever seen in astronomy, every galaxy image, every deep field survey, every faint glow from the early cosmos, exists inside a vast but finite bubble of information. A bubble defined not by walls or edges, but by time and motion. The idea feels counterintuitive at first, because when we look up at the night sky it feels endless. Yet physics asks us to slow down and notice something subtle. Light is fast, but it is not instantaneous. The universe is old, but not infinitely old. And space is not static. It stretches while light is traveling through it. These three facts together quietly create a horizon. Not a dramatic barrier, not a cosmic wall, but a limit on what information has had time to arrive here. That limit is what we call the observable universe. A useful way to feel this rather than merely understand it is to imagine standing on a beach at dusk. The ocean appears to meet the sky at a clean line. You know the water continues beyond that line, yet your eyes cannot confirm it. The horizon is not an edge of the ocean. It is an edge of visibility. In cosmology, the observable universe plays the same role. It is not the edge of existence. It is the edge of what light has been able to show us since the beginning of cosmic transparency. Early in the universe, light could not travel freely. Space was filled with a hot, dense plasma that scattered photons again and again. Only after hundreds of thousands of years did atoms form and allow light to move through space without constant interruption. The faint afterglow of that moment is still visible today as the cosmic microwave background. It marks a screen at the edge of our vision, not because nothing existed before it, but because light could not yet carry information in a way we can now detect. This is why the observable universe is often described as a bubble of light. It is a region carved out by physics, not by imagination. Carl Sagan famously said that we are made of star stuff. This sentence resonates because it connects our bodies to cosmic history. But within the idea of the light bubble, it takes on an even deeper meaning. Every fact we know about stars, galaxies, and the early universe comes from photons that successfully crossed space and time to reach us. Knowledge itself is limited by which messengers survived the journey. Neil deGrasse Tyson often reminds us that the universe is under no obligation to make sense to us. When we understand cosmic horizons, this statement stops sounding discouraging and starts sounding precise. The universe does not hide truths out of malice. It simply follows rules that place some information forever outside our causal reach. To picture this, imagine an ant walking across the surface of a balloon that is being inflated. The ant walks at a steady pace, always moving forward. But the surface itself stretches beneath its feet. Some distant points on the balloon move away faster than the ant can walk toward them. No matter how long the ant walks, it will never reach those regions. Light behaves in a similar way in an expanding universe. Even at its incredible speed, there are regions of space whose distance increases faster than light can close the gap. This does not violate relativity, because nothing is locally moving faster than light. It is space itself that changes the game. Stephen Hawking once urged us to remember to look up at the stars and not down at our feet. When you realize that every star you see is ancient light arriving just in time, that advice becomes almost meditative. Looking up is not only an act of curiosity, it is an act of reception. You are receiving messages that began their journey long before humanity existed. And you are receiving them only because the geometry and history of the universe allowed them to reach you. Examples from everyday life help anchor this idea. Imagine two people shouting to each other across a landscape that is slowly stretching apart. At first, their voices travel easily, but as the distance grows and the air thins, the sound fades. Eventually, no matter how loudly they shout, the message cannot cross the gap. Or imagine living in a valley surrounded by mountains. Villages beyond the ridges still exist. Their lives continue, but their signals never reach you. The cosmic horizon is like that ridge, except it is built from time and expansion rather than rock. The observable universe therefore becomes a careful definition. It is not everything that exists. It is everything that has been able to influence us so far. In everyday language, the word universe often means all that is. In observational cosmology, it means all that is observable from here and now. These two meanings overlap, but they are not identical. Confusing them leads to unnecessary paradoxes. Separating them leads to clarity and humility. Modern cosmology does not require the universe to end where our observations end. In fact, many well-motivated ideas allow the universe to be vastly larger than the observable region. Even without leaning on speculation, the core conclusion remains solid. Observation is limited by causal structure. There are places whose light will reach us in the future, and places whose light never will. The observable universe is therefore dynamic, not static. It changes as time passes, but it will never expand to include everything. This realization reshapes not only astronomy, but philosophy. It tells us that reality does not owe us completeness. And yet it also tells us something hopeful. Within this finite bubble of light, there is already more structure and beauty than any single mind can fully absorb. Billions of galaxies, each with billions of stars, all revealed by photons that happen to arrive here. Mystery does not diminish this achievement. It frames it. There is a quiet dignity in accepting limits that arise from the universe itself rather than from human failure. Science does not end at the horizon. It becomes more careful there. It distinguishes what can be tested from what can only be inferred. This discipline is not weakness. It is strength. It allows us to say with confidence what we know, and, with honesty, what we may never know from this vantage point. When you look at a galaxy billions of light years away, you are not seeing it as it is now. You are seeing it as it was when that light began its journey. In this sense, the observable universe is a time archive, a layered record of cosmic history centered on us not by importance, but by circumstance. Each shell of distance is a shell of time, and eventually, the archive reaches a page where light could no longer write clearly. Not because nothing existed before, but because the conditions did not allow readable messages to travel. So, when we say that what we see is only a bubble of light, we are not shrinking the universe. We are acknowledging how extraordinary it is that any part of it can be known at all. Every image is a victory over distance and time. Every measurement is a conversation that succeeded against cosmic odds. And beyond the bubble, reality may continue in silence. Not empty silence, but unreceived silence. This understanding invites a final and unsettling question. If the observable universe is only a fraction of what exists, how many answers do we mistake for ultimate truths, simply because the rest of reality has not had time or permission to speak to us yet? What if the greatest wall in science is not a lack of intelligence, but a lack of light? Every telescope we build, every detector we cool down to near absolute zero, every equation we trust, must ultimately bow to one quiet fact. The universe only tells us what its light can carry to us. That limit is not a minor inconvenience. It is a fundamental boundary that shapes what we can observe, what we can measure, and what we can honestly claim to know. We do not watch the universe as it is right now. We watch it as it was when the light began its journey. When you look at the moon, you are seeing it a little over 1 second in the past. When you look at the sun, you are seeing it minutes ago. When you look at the Andromeda galaxy, you are looking millions of years into history. This is not poetry added onto physics. It is the operating system of astronomy. The deeper we peer into space, the further back we fall through time. And then the horizon appears. Not a line you can point to in the sky, but a limit written into space-time itself. There are regions so distant that even if they shine forever, their light can never reach us because the space between us and them expands too relentlessly. This is why the scientific method in cosmology is both powerful and humble. We can test ideas by comparing predictions to light that arrives here, now, in our detectors. But we cannot demand evidence from a realm that is causally disconnected from us. In that sense, the limit of light becomes the limit of verification. It tells us where confidence ends and where speculation must be clearly labeled as such. Consider a simple example, like trying to reconstruct a city from postcards that arrive years late. You can map streets, infer landmarks, notice patterns of growth. Yet you can never claim you know the city today without fresh deliveries. Our universe is like that, except the delay can be billions of years, and some postcards will never arrive at all. This is why missions that, to capture ancient light, feel like time machines. Because they are. The cosmic microwave background is a thin veil of leftover radiation from the early universe, and it serves as a boundary marker for how far back light can carry reliable information about structure and conditions. Even our boldest claims must respect this boundary. We can measure expansion by reading redshift in ancient light. We can estimate cosmic ages, and we can test models of how galaxies form. Yet beyond the observable limit, We cannot directly sample what is there. Albert Einstein called the most beautiful experience the mysterious. And cosmology lives inside that sentence. Carl Sagan reminded us that we are a way for the cosmos to know itself. That knowing is not infinite. It is local, hard-earned, and disciplined by horizons. Stephen Hawking observed that we are an advanced breed of monkeys on a minor planet of a very average star. And yet we build instruments that read the universe back to its earliest chapters. So the limit of light does not weaken science. It clarifies it. It forces better questions, sharper tests, and more honest language about what data can truly decide. And perhaps that is the most meditative lesson of all. That reality is not obligated to be fully available to us. We learn from what arrives. We doubt what cannot be checked. And we keep listening to the sky with patience. Because every photon that reaches us is both evidence and invitation. What if the universe is so vast that most of it will remain forever beyond the reach of light and knowledge? Not because we failed, but because nature built a boundary we cannot cross? That single thought can feel like a cold wind in a limitless night, yet it can also feel like an invitation to awe. Because the moment you accept a horizon, you begin to understand what science truly is. Not a claim of total ownership over reality, but a disciplined way of listening to what the cosmos is able to tell us. Imagine standing on a beach and watching ships slide toward the edge of the sea. Not because the ocean ends there, but because your sight has a limit. The cosmic horizon is like that. Except, the sea itself is growing while you watch. Some galaxies are not merely far away. They are being carried away by the expansion of space so quickly that any light they emit today will never reach us. It is as if the universe is sending messages in bottles. And beyond a certain distance the current is so strong that the bottles drift outward forever. This does not make the universe smaller. It makes our moment of connection more precious. Edwin Hubble once wrote that man, equipped with his 5 senses, explores the universe around him and calls the adventure science. Notice the word adventure, because an adventure is not guaranteed to end with a map of everything. Carl Sagan gave the same spirit in a simpler way. Somewhere, something incredible is waiting to be known. The horizon does not cancel that promise. It sharpens it. It tells us that every photon that reaches a telescope is a gift from a past we did not witness, yet can still understand. And there is a quiet discipline in that understanding. Stephen Hawking urged, "Remember to look up at the stars and not down at your feet." Looking up is not denial of limits. It is respect for them. When we study the cosmic microwave background, we are reading light that has traveled since the early universe. When we measure distant supernovae, we are watching the expansion write its signature across space and time. These are not small achievements. They are triumphs of patience, mathematics, and imagination working together. So does an unreachable universe make science feel small? Only if we confuse science with conquest. In truth, the existence of boundaries can make the human journey larger, because it transforms curiosity into character. We become a species that learns to build meaning without needing to possess everything. We learn that the observable universe is not a prison. It is a window. And if beyond that window there are regions we will never touch, then our responsibility becomes clearer. to care for the fragile world that can ask such questions at all. In the end, the horizon is not an insult to knowledge. It is the reason knowledge matters. If most of reality will remain out of reach forever, why do some people still speak as if they already know the final answer?